The paper titled, Emo Pilarsamo Pi. Knowledge Distillation to Support Fine-Grained Context-Aware and Context-Less Emotion Classification, by Alexander Shvets addresses key challenges in emotion classification for natural language processing. It begins by highlighting how most datasets for sentiment analysis often lack the necessary context in which an opinion was expressed, making it difficult to accurately understand emotions. This is especially true for fine-grained emotion categories, where subtle nuances matter. The authors point out that foundation large language models, like GPT-4, tend to overpredict emotions and require massive computational resources, which isn't practical for many applications. To tackle this, the researchers designed an innovative pipeline for synthesizing data using a large language model called Mistral 7B. This model generates training examples that can be used to fine-tune more efficient, lightweight models based on BERT-type encoders. The main goal is to increase the semantic diversity of these examples, ensuring they're not repetitive and cover a wide range of scenarios. They achieve this by grounding the generation process in a corpus of narratives, which means drawing from stories to create utterances that are centered around characters and unique contexts. This approach allows for the production of non-repetitive texts across 28 different emotion classes. In their experiments, they ran about 700,000 inferences, which took around 450 GPU hours, to create a new dataset. This dataset includes 100,000 contextual examples, where the emotion is tied to specific situations, and 300,000 context-less examples, which focus on standalone utterances. By doing so, they cover both scenarios. One where context is crucial and another where it's not. These examples were then used to fine-tune pre-trained encoder models, resulting in a series of models called Emo Pilarsamo Pi. The paper demonstrates that these Emo Pilarsamo Pi models are highly adaptable to new domains. For instance, when tuned for specific tasks, they perform exceptionally well on datasets like Go Emotions, ISEAR, IEMOCAP, and Emo Context. In fact, they achieve state-of-the-art performance on the first three of these. Go Emotions is a dataset with a broad range of emotions from social media. ISEAR deals with self-reported emotions from everyday experiences, and IEMOCAP involves multimodal data from conversations. This success shows how the models can handle both text-only and more complex inputs. To ensure the quality of their dataset, the researchers conducted thorough statistical analysis and human evaluation. They examined aspects like utterance diversification and context personalization, confirming that their methods successfully created varied and personalized examples. However, they noted some limitations, particularly for the neutral emotion class, where diversification was less effective. Additionally, they pointed out the need for better handling of labels that fall outside the predefined taxonomy, meaning emotions that don't fit neatly into the 28 classes. Delving deeper into the introduction, the authors discuss why manual tagging of texts for emotions is so challenging. It's a burdensome process because emotions can be expressed in countless unpredictable ways, and the same utterance might evoke different emotions depending on the context or the person's personality. This leads to inconsistencies in annotation, especially for fine-grained schemes. They reference studies like those by de Villers and colleagues from 2005, which highlight these issues. Most existing datasets use overly broad emotion categories, with few exceptions that attempt finer granularity, but even those often ignore context. The paper contrasts this with the capabilities of foundation models like GPT-3.5 and GPT-4, which can handle contextual tasks without specific tuning. However, these models struggle with accurate emotion understanding, as shown in recent works by Wang and others in 2024. This is where synthetic data generation comes in, using LLMs to create more training data and address scarcity. But as the authors note, this method has limitations, particularly in generating diverse data for subjective tasks like emotion classification. Models often produce similar outputs, leading to a lack of variety. To overcome this, the researchers propose a combination of techniques. They focus on enhancing diversity through special prompts, incorporating real-world examples in a few-shot learning setup, and adjusting parameters like temperature to balance creativity and realism. Their key innovation is grounding the generation in narratives, which helps produce more unique, story-based utterances. This is crucial for massive inference tasks, where repetition can skew results. In terms of methodology, the data synthesis pipeline is built around Mistral 7B, a capable yet more accessible model compared to giants like GPT-4. By leveraging this, they distill knowledge from a large model to smaller, efficient ones, making emotion classification more feasible in resource-constrained environments. The generated dataset not only enlarges the semantic diversity but also ensures that examples are tailored to specific emotions, with contexts that mimic real-life scenarios. The results section provides evidence of the model's effectiveness. For example, on the Go Emotions dataset, the Emo-Pillar-Samo-Pi models outperform previous state-of-the-art by accurately classifying a wide array of emotions from online posts. On ISEAR, which collects data from people's emotional experiences, the models show strong generalization. For IEMOCAP, involving dialogues from acted scenarios, the models handle the contextual elements well. Emo Context, another dataset, tests context-aware classification directly. Human evaluation played a big role in validating the dataset. Participants assessed the diversity and relevance of the generated utterances, confirming that the pipeline succeeded in creating personalized contexts. Statistical analysis, such as measuring variance in language patterns and emotion distributions, supported these findings. However, the authors candidly discuss areas for improvement, like better management of out-of-taxonomy labels, emotions that don't align with the defined classes, which could lead to misclassifications in the pipeline. Overall, this work contributes significantly to the field by providing a large, diverse dataset and efficient models that bridge the gap between context-aware and context-less emotion classification. It underscores the potential of knowledge distillation and synthetic data in advancing NLP tasks, while calling for ongoing refinements to handle the complexities of human emotions.